previously we have discussed in last lecture that series RC circuit, parallel RC circuit, right? And quickly I will go through. And this was the series RC circuit. And for the series RC circuit, we drawn this, vector diagrams. You can see this is voltage vector, and voltage vector is basically for the series, because in series voltage is different. So we have voltage vector, but not the current vector, because current is same in series, we know that. So all will be in the same direction. That's why. And for the parallel, we know that the current is different. So we have current phasor for parallel circuit. So this is parallel, and we have current phasor for that. So IR is here and IC is here. This is something. So now we know that all these things, and we also know the impedance concept discussed already. And this is a sinusoidal response. So here we discuss the reciprocal of G, B, C, and Y, and this Ohm's law formula in terms of admittance. And yes, and now this is just for review, like sine, cosine, and tangent. Now this is conversion from parallel to series. It is like, we have given a parallel circuit and we want to find its equivalent series circuit. Okay, it's so simple to find it. So there is a way to do this one. So what you need to do for the given parallel circuit, first you need to find the impedance, okay, and you have to find the phase angle for the given parallel circuit which you want to convert it into series. So this is something to obtain the equivalent series circuit for the given parallel circuit. First find the impedance and phase angle of the parallel circuit. All right, parallel circuit. Then we will use this Z and theta which we just calculated to construct an impedance triangle shown in this figure. So this is something like that. So we can do this one. We will calculate first R equivalent, which will be the series equivalent of the parallel circuit, resistance. So Z cosine theta. Then X equivalent will be calculated, Z sine theta. And this is basically the impedance triangle for the parallel circuit, but now it is converted into series. So it is an equivalent series circuit, So R equivalent will be calculated this formula, and we can get this. Okay, so let's have an example how the question come and how can we solve this one. So we have given a parallel circuit, and now they are asking convert the parallel circuit to obtain a series form, okay, equivalent series form. So as I just told you, first of all we need to calculate Z, then we need to calculate theta, then we need to apply the two formulas which were written backside. So theta, how can we find the Z? There are two ways. Either you can go for these concepts which we know, calculate the conductance, then what is that, susceptance, then calculate the admittance, then calculate this one. Or can we directly calculate the Z for the parallel? If yes, what is the formula? Do you remember? Z is equal to
RXC.
RXC.
The square root.
Very good.
Of R squared plus XC squared.
XC squared. That's it. So it's so easy, right? And theta, what will be the theta? Tan inverse
of R over XC.
Absolutely right. It is parallel. That's why R over XC, right? So this is something. So now you can directly calculate this way, or you can calculate. So this, which one is easy? I think this one is more easier. You can just quickly put this one and calculate Z and theta rather than calculating G, B, C and all. Okay, right? Yeah. So once you get it, that's what I need to do. I need to calculate R equivalent. Okay, which is what? Z cos theta. Then I will calculate XC equivalent, which is Z sin theta. That's it. Once you get these two things, you can draw this circuit or for the given parallel. This is the series. This is the resistance and this is the reactance, capacitive reactance. Clear?
Yes.
Okay, so this is possible. All right. So now the thing is actual circuit. Yani, in reality, the circuits is like basically a combination of series and parallel. So how to deal in this situation? Like if you remember, we discussed series circuit for the resistance, then we discuss parallel, then we discuss combination. So same is happening here. We discuss RC series, RC parallel. Now this is series parallel combination circuit. So both are there. So if this type of question I gave you and I ask you girls calculate the total current.
Need to convert the parallel into series.
Yes, we need to convert things because total current here, because it's a series, how would we combine this Z and Z2, because this Z is this is parallel, this is series. So the way is that we will do one thing, we will convert this yellow into series. When we convert it into series, so this circuit will look like this, battery. So this way, this is what R1, C1, or we can say XC1, and this is what R2, because after conversion equivalent definitely. This is, we will be getting XC2 equivalent. Now this is complete series circuit this way. So we can say how much is total? RT, which is what? R1 plus R2 equivalent, right? Similarly, what is next? XCT total. So it will be XC1
XC equivalent.
Bus 2 equivalent. And we know that capacitive reactance will be treated like a resistance, simple addition. So once we get these two, can we calculate Z total now?
Yes.
Yeah, how can we calculate Z total? It's a series circuit, right? What should be the formula?
Yes, the square.
Calculate the Z. Very
RT.
good, because it's a series circuit. Yeah, RT square plus XCT
squared.
Bus. So now I know the total impedance. So can't I find the I total? What's that? VS best Ohm law. So total voltage supply divided by the total impedance. This is the way. Easy. So this way we can solve the questions. So let's see one example where we will be we need to find the total values. All right. So it's just mentioning how to calculate Z here, how to calculate Z for the parallel. We know that all these things. Now, so this is the circuit. So they are asking to calculate total impedance, asking to calculate total current, which I already explained to you. All right. Then what last? Phase angle by which I total leads the VS. So, okay, just a minute. If I go back, if I do undo, I don't know, undo will work here. No, redo. No, it will not work. So, alas, leave it. So, 2 points, point A, point B, I already explained to you. Point C. Point C can also be calculated. Theta, what it should be? Theta, because we after conversion we will be getting a simple what XCT over R RT, correct? This is the formula, because total will be using, right? So this is the way to do this one.
Doctor, why R over X?
Y R over X. Okay, just a minute. I'll let you know. Just a minute. Actually, I have a call from college. Yes. So, girls.
Yes.
Should I start now?
Yes, you can.
Okay. So yeah, we actually I got a call from college, so I need to pick. Okay. So we were discussing about, someone asked me why this XC over RT. Okay. So this is why I'm writing this one, because we have converted this one. I was considering that we have converted this one. So once we have converted that one, so what is your actual circuit? Your actual circuits become now series because it is already in series, and we have converted this one. So what is overall circuit? That becomes the series circuit. So let's say this is the formula for the series circuit to find the phasor angle, phase angle. Correct?
Yes.
Did you get my point? Okay, because we converted this parallel into series, and this is already in series, so we added series component, then that's why. Okay, let's just wait. A solution is there, I will explain. So see now, so very first thing is that because we have C1 C2, so what we need to do, we need to find first XC1 and XC2. So we did this one. Then what is the next step which I should do after getting XC1 and XC2? The next step is gonna be, I'm just writing the steps so that any picture will be clear in your mind how to proceed this type of question. So very first thing, when you have this one, maybe usually we can give you this XC1. So if given, it's good. If not given, you have to calculate XC1, XC2, calculate it. After calculating, what you need to do, you have to focus on this parallel. Yeah, correct. We need to calculate Z1 and Z2. But see, actually, I don't need Z1. I will tell you later on. I need only Z2 so that I can convert, because I need to convert this one. So Z2 can be calculated by the formula product over vector sum. Yani R2 multiplied by XC2 over R2 square plus XC2 square. Correct. So this way I will get Z2. Similarly, I can get theta 2 or what I can say theta p, yani for the parallel circuit, theta p or theta 2, whatever I can give the name. So theta p, what it will be now? Tell me the formula. Tan inverse, what it should be? All right, correct. R2 over XC2, absolutely right, because it's a parallel circuit, so it should be R over XC. So okay, now once I get it, what should be my next step?
Find the R equivalent.
Find the R equivalent, absolutely right. So R equivalent, which should be Z2 cos theta P. Now XC equivalent, what it will be? Z2 sine theta P. Yeah, so this is, after getting this one, now I know the series equivalent of the given parallel. So my circuit will be look like that, which I drawn previously, right? I am not again drawing that one. So you know now. So the time is to calculate the total resistance, total reactance. So total, yani let's say RT, R1 plus R equivalent. Similarly, what? XCT, total reactance, XC1 plus XC equivalent. Finally, Z, okay, or we can say, or even we can say Z, because another Z1 is written, it's like Z, so total or whatever is Z. And because this is RT for the series, this is for the series, so formula is gonna be RT squared
plus XC total squared.
Yeah, this is something now. So we have given answer of first part this way. Second part, total current. So total current is what? Ohm's law.
V over Z.
Yes, Vs over Z. This is something. Now, final option part, phase angle. So phase angle, yani theta.
XC over R.
XC T.
Yeah, total.
Oh, no, no.
R total.
Yeah, total. Yeah, this total, right? Over R total. That's it. So this is the steps actually, and you people should also practice this way. If you are not doing, you should do this way, because even if you make a mistake somewhere, you will be getting marks because of your concepts is showing by these formulas, and you calculated something. Okay, so at least marks will be given, partial marks you can get for that. So this is the process overall. So you can take a screenshot, and solution is there, by the way. You can see the solution also. So this is possible for this type of questions. So this is there. So see, they are using B, G and all. I don't need this one. I can directly calculate, simple. So this is Z2 calculated R equivalent, RC equivalent, right? Then R total, XC total, then Z total. That's it. After Z total, they calculate the total current, Ohm's law, calculated the same. All right. So this is the way to solve this type of question. Okay, so the last thing which is remaining in this chapter, it's about the power. Okay, so until now, how many types of power we have discussed? The true power, which is associated with the resistance, and it is because of the resistance get heated and it consumes the power. In case of purely capacitive circuit, we know that there is no true power, but there is a reactive power, yani the rate at which it's take energy and return back the energy, that's called reactive power, and the unit is VAR. Now girls, the circuit which I just discussed this one, so here we have resistance, here we have capacitance, so both are there. So both type of power is there, like true is also there, like reactive is also there. Am I right? Getting point?
Yes.
Okay, so what is the name what name should be given to the total power or overall power? So the new name is going to be introduced now, that we call apparent power. Apparent power. Okay, so apparent power is basically is the combination of the true power and the reactive power. But in order to calculate that total power, it's not like that we will just add true power plus this power and we have again here is a vector sum. Okay, and it is like apparent power will be calculated by the vector sum, any under root true power square plus reactive power square. Now, so this is all about the power. So this is they are just writing what I just explained to you here. You can read it later on. This is just showing how a capacitor, charge half cycle and return the energy to another half cycle. So just a screenshot from the fallstat.com to see this one. Okay. So here is clockwise direction, blue one is anti-clockwise direction. All right. See now the powers. So true power formula, well known, and it is the formula because it is associated with the resistance. Reactive power associated with the capacitor, so we need a reactance here, capacitive reactance, right? So last is remaining apparent power. Okay, I'm also writing that one. P apparent power PA, and it is given by under root square P T square in a total square plus PR square. It is a vector sum of these two powers. So this is not only the formula, another formula is that because it is a total power. So how can we calculate the total power? Total V and total current. Do you remember the formula? P is equal to V into I?
Yes.
Yes.
So it is the same because it's a total power, V into I. And what is the unit of this? The unit is volt ampere. Because the unit of voltage is volts, current is ampere. This is the unit volts ampere. True power, watt. Reactive power, VAR. Getting the point?
Yes.
Okay. This is also calculated PA. Yeah. So this is the formula. Okay. So this is not just a formula. There is one more formula corresponding to the related to the power factor, which is we'll discuss in the next. So see the next slide. Next thing is power factor. And what is a power factor? Power factor is a relation between apparent power, which is volt ampere, and true power in watts. So volt amperes. multiplied by the power factor equal to true power. Okay, what is it? PT, true power, not total, true power, is equal to apparent power, yani PA, multiplied by the power factor. What is power factor? Power factor given by cos theta. Cos theta. So this can also be calculated. 2 power is equal to VA cos theta. And what is PA? PA, you know that it is V into I. Okay, now theta is the phase angle actually. So now theta is, if we are having a purely resistive circuit, then if there is no capacitance, so what will be there? In purely resistive circuit, what will be the phase angle, girls? If we have purely resistive circuit, what should be the value of what is that? Phase angle?
0.
Very good, 0. So if we put here 0 in this formula, so what it will be? Cos 0. And do you know cos 0 is what? Cos 0 is 1. It's 1. So at this time, P true will be VSI total. Why? Because what is PA? PA, I already told you, it is VS into I cos theta, which can also be written like this. So this factor will become 1, and P true at that time will be like that. That's why I said, do you remember this formula? So this formula everyone knows. We know this one. We know this formula. Why? Because of the theta is 0. So cos theta value will become 1. So we have this formula for the purely resistive circuit. You know that one. Also, if we have purely capacitive, so purely capacitive, do you remember the phase angle for the purely capacitive?
It will be 90.
It will be 90. Yeah, we know that voltage and current is always out of phase 90. So if we put 90 in this formula, you will know that cos 0 is like this one. So what will be the true power?
0.
0. Because there is no true power, there is no resistance, only reactive power is there. Okay, that concept is also explained here very well. So this, this type of question may ask, we can just puzzle something, we can ask you, so girls, for this given formula, find that, what you call, for a purely resistive circuit, what should be the true power? So any concept has to be clear. So because of this, theta depend upon the type. If it is purely resistive, it will be 0. If it is purely capacitive, it will be 90. And now this is the mixing now, what we are learning here. So when mixing, so definitely it will be having some value and we can calculate it. So let's see some question to understand how this could be asked. So apparent power, I already told you. This we can draw the apparent, what you call phasor triangle for that. So P true will always be in the direction of the VR. Do you remember? This is always VR, and this is what? VC. Okay, and this is what? VS. So VR, yani resistive voltage. So resistive power, which is true. Capacitive voltage. So we have reactive power there. This is overall yani voltage. So here we have apparent power, and these are the units of it. And this is the theta, which we know. Theta is what? True power, and this apparent power angle. All right. So apparent power is something which can be calculated. Or see this question. So determine the power factor and the true power. Okay. So tell me the steps first. XC, very good. The very first thing is XC. All right. After XC, power factor we need, right? So for power factor, what we need?
The phase angle.
Theta, phase angle, correct. So tan inverse XC over R, right? XC over R. After getting this, PF, power factor, cos theta, we can get whatever is the value, no problem. So we will finish this one, right? Yeah. Next is what? True power. Okay, true power, yani PT. And true power is what? I square into R. We can calculate this way. We can calculate. Is there any other way to calculate the true power?
Yes.
What is that one?
We can find Z.
See, do you remember this formula? P2 is equal to, what is that?
A cosine theta.
Cosine theta. Yeah, this one. So theta value, what is coming? But see, again, we need to know I total, but we don't have I total, correct? So I total we can calculate by calculating Z, as you just mentioned. Yeah, so Z we can calculate first. R square plus X square. Once you get it, simply it is easy to calculate IT. What is IT? IT is VS over
Z.
S. Just get it, then put in this formula, and then you can, or you can apply this formula also, correct?
Yes.
Yani by using cos theta or by using this one, whatever, value will always be same. Okay, so there are different ways, different formulas, but whatever suits you, whatever you feel is striking in your mind, you just go for it and calculate it. So this is the solution. So this is XC first, then theta, then power factor, then Z, then I calculated, then they use true power VSI in this one, and they calculated this one. And this one can also be calculated this way. Okay. All right. Now, what is there next? So this is for circuit, true power. Again, they are asking true power, reactive power, and the apparent power. Okay, this is something. And XC has been determined. So they are telling already XC is 2. All right. So see the solution now. So you can calculate Z total. Then you can calculate I this way. After calculate theta, then P true. We know that this is the way, or we can use this one, whatever feels, you can use it. Then PR will be I square into XC. PA is equal to I square into Z. Then we can also calculate apparent power by using this formula, which will give you same value. You can see this one, either this I square Z, or by knowing P true square plus PR square, because we know the triangle. All right. So clear to all of you? Any doubt related to that one? All right. Okay. So this chapter, I believe we have completed this chapter, and yeah. So Roba, what is the meaning? Is this? I don't understand. Very clear. What is this? Or very good? Clear. Okay. How is pronounced? Wamas. No problem. By wrong. It means it's wrong.
Yeah, she meant to write in English, but her keyboard was in Arabic.
No, I know that. This is clear because sometimes keyboard is like that. This is okay. So, okay, so we have done this chapter. All right. So here is advice to you. These two chapters, chapter number 9 and chapter number 10, you people should revise, before we start chapter number 11 and 12. So I'm not going to start 11, 12. It is because of, yeah, I know this one. So because of that, this lab is actually designed in a way we have experiment related to the other chapters rather than this chapter. So we need to start as per the syllabus, chapter number 16 now. See this one, okay? Then we start 11, 12, 13 later on, because of the labs are according to that one, okay? So this is like that. So, but there is a very good thing. These chapter, 11 and 12 and 13 even, at least 11 and 12, they are exactly similar to the chapter, these two chapters. Capacitors and inductors, these two. This one, a capacitor and RC or inductor and RL. There will be a minor change only. So when I start this 11 and 12, you need to just revise these two chapters so that quickly you can link and we can finish them. So now we will start new chapter, which is about diode and applications, and it is basically